G'day guys, and welcome to our introductory lesson on light. Let's discuss first of all the qualitative properties of light, so just a general description of our experience with light in the universe. First of all, light tends to travel in a straight line when it's not moving through small gaps or around small objects. And it tends to also travel at a constant speed, so v equals c, and this occurs in a vacuum here. When light is travelling in a medium that is not in a vacuum, that's when the speed will dip. So the speed of light will actually be less than c. But in a vacuum, the speed is constant, and c is around equal to 3 times 10 to the 8 meters per second. And this speed is actually due to the fact that light is electromagnetic radiation. So light is caused by oscillating waves in the electrical field and in the magnetic field. These waves oscillate in a transverse fashion, and light has to travel at this speed in order for those two oscillating waves to support each other indefinitely. If light does have a constant speed, and we can say since light is a wave, that it has this wavelength here, then we know from sound that the velocity of sound is equal to the wavelength times the frequency. The same goes for light. The speed of light is equal to the wavelength, which we measure as a distance, so in meters, multiplied by the frequency of light. And we can calculate the frequency of light by dividing c by lambda. So let's discuss for a second, if these are the two defining features of light, the frequency and the wavelength, where does the visible spectrum of light fall? Because light can go from anything, what's the lowest? The lowest, I think, are radio waves. Radio waves have incredibly huge wavelengths. And the shortest wavelength, I think, is an X-ray. There might be something beyond X-ray, I'm not sure what it is. But the fact is, light can have many, many different wavelengths, and as it changes these wavelengths, it actually changes its property. But the light we see has a wavelength in a range of between, I have 390 nanometers and 700 nanometers, so I'll draw my scale here. This is the wavelength. And between 390 nanometers, that's 10 to the negative 9 meters, and 700 nanometers, we can see visible light in here. Similar to the way our ear can only pick up certain frequencies of sound, our eye can only pick up certain frequencies and wavelengths of light. So if these are the wavelengths between which we can detect visible light, let's see what frequencies we can detect. So we know the wavelength here is 700 nanometers. And we set up here, you can work out the frequency by dividing the speed of light by the wavelength. So frequency is equal to c on lambda, which is 3 times 10 to the 8 on 700 times 10 to the negative 9, which is equal to 4.3 times 10 to the 14 hertz. And hertz is the measure of frequency. Sorry, I should have put that in. Frequency is in hertz. And it's another way of writing seconds to the negative 1. So this is the frequency that corresponds to this wavelength of 700 nanometers. I'll put that in. Frequency in hertz, 4.3 times 10 to the 14. Let's see what frequency corresponds to 390 nanometers. Frequency equals speed of light on lambda equals 3 times 10 to the 8 on 390 times 10 to the negative 9, which comes to 7.7, around thereabouts, times 10 to the 14 hertz. 7.7 times 10 to the 14. And as you can see here, as the wavelength becomes bigger. 700 is bigger than 390. The frequency becomes smaller, which makes sense because if our wavelength does become smaller like this, we expect more troughs to pass a point per unit time. So wavelength bigger, frequency smaller. So in actual fact, I'll reverse the direction of this arrow. Whoops, put it over here. And it also tells us we can see light. If we can see light that has a wavelength of between 390 nanometers and 700 nanometers, we can also see light that has a frequency of between 4.3 times 10 to the 14 hertz and 7.7 times 10 to the 14 hertz. Let's discuss for a second. No, actually, let's continue on that thought. We said before that radio waves have an incredibly large wavelength. If the wavelength is large for a radio wave, the frequency must be small. And we also know that X-rays have an incredibly small wavelength. And if the wavelength is small for an X-ray, the frequency must be large. So moving on, let's discuss coherent and incoherent. Coherent and incoherent. So coherent light basically says that if light is made up of packets of energy called photons, and each of those photons has its own wave, in coherent light, the waves exactly match up, like so, as they're travelling. In incoherent light, the wave of one photon might be muddled with the wave of another photon, and none of them really match up at all. Coherent light is the light we use for a lot of experiments, because it's very useful knowing that we're not going to get any kind of interference since the light is cooperating with itself perfectly. Okay, now we'll talk about power, energy, and intensity. The energy is the amount of, we'll say light energy in this case, delivered to a surface over time. So in this case we'll say, hey, 50 joules was delivered over a time of 10 seconds, and this plane here has an area of 2 meters squared. So energy is the total energy delivered to this surface over a specific period of time that we can name. Power is equal to that energy over the time, and it's given by watts. If energy is in joules, power is in watts per second. Sorry, power is in joules per second, which is in watts. So the power being delivered to this sheet is equal to energy over time, that's 50 over 10, that's 5 watts. And finally, intensity is equal to the power over the area, so that's watts per meters squared. 2 meters, whoops. Area equals 2 meters squared. I hope I got that right. 2 meters squared. Been doing too much projectile motion recently. So intensity is equal to the power over the area. In this case, that's 5 on 2. That's 2.5 watts per meter squared. So we can start to calculate how much energy light delivers per second. And if we know the intensity of light, so the intensity of light that is arriving on a square meter patch of field somewhere, if we multiply the intensity by the area, we can figure out the amount of power that's reaching a large surface per unit, the amount of power that is reaching a large surface, or the amount of energy per unit time. So if we're going to find, say, we have a solar panel, and we put that solar panel out in the sun for 5 seconds. If we know the intensity of that light reaching that solar panel, we can multiply by the area to get the power, and finally by the amount of time, and we find how much energy that solar panel did absorb, provided it is operating at 100% effectiveness. We can dream. So now we can talk about a few of the interactions of light and matter. Scale this down. So when light does meet matter, I think there's 3 broad categories. You can either have a reflection, a transmission or an absorption. So in a reflection, the light bounces off a surface. And the law of reflection states, if you've got this line perpendicular to the plane that is reflecting the light, this angle of incidence must be equal to this angle of reflection here. And this sort of comes in, excuse me, this comes intuitively to most people because this is the kind of thing you see when you play billiards and you bounce a ball off a surface like that. It behaves in a predictable way. Not only is that's perpendicular, this angle here equal to this angle here, but that is the same as saying this angle down here is equal to this angle down here. So that's reflection there. Now transmission. Say light was going through a prism, like a diamond or a chandelier. It comes in like this. We'll say this is air. And as it reaches the glass medium, it'll bend towards the normal line, the perpendicular line there. So that light now has a bend. And then it moves out like that. So before we said light travels in straight lines. Light will travel in a straight line as long as it's staying in the same medium. If it changes medium, it'll bend. And a good example of this is when you're driving along the road and you're looking ahead. You see this illusion, a mirage. And what it is this wet appearance on the road. It's almost like there's a pool of water on the road ahead of you. What you're actually seeing is the light moving through hotter air and bending, and you're seeing the reflection of the sky on the road ahead of you. And this is the principle behind it. We have this idea of a refractive index. Let's say the refractive index out here is N1. This medium has a refractive index of N2, and then here it's N1. The refractive index tends to be higher in things like glass and jewels compared to air. And what it tells us is if the light is moving at a certain velocity here, and also N2 is greater than N1, so the refractive index of N2 is that of, say, glass, and N1 is that of air, then the light changes speed as it enters this medium, and then accelerates again as it leaves. Since the light is changing speed, since N2 is greater than N1, V2 is actually less than V1. So the higher the refractive index, the lower the velocity. And with that change of speed comes this change of direction. And when it leaves the medium, it continues in the same direction. But of course, see, it's been shifted over, which is part of the reason why you get that strange, when you're in the bath and you put your arm under the water, your arm seems to bend if you're looking down at it. It's because of this refractive index. So that's what happens when light is transmitted through a medium. It tends to bend it a little bit. Finally, absorption. This is when you have, we'll say, an atom of hydrogen, and you have an electron sitting at a certain energy level. We will say in physics it's orbiting the nucleus. It's not really orbiting the nucleus, it's sitting around it, but we'll say it's orbiting. When the light comes in, it strikes that electron and it bounces that electron up to a higher energy level. And the light is absorbed, and that energy, since the total energy of the universe can't change, that energy that the light had was used to move the electron to a higher energy level. A lot like gravitational potential energy. It takes energy to move a box out of the Earth's gravity. It takes energy to move the electron away from the positively charged nucleus. So I think that pretty much covers... Oh wait, gosh, we haven't got much room here. I'll delete this power section. The last thing is diffraction. So we said light behaves like a wave. Let's draw a little gap here. These are light waves meeting a wall here with a small gap in it. As the light passes through this gap, it behaves a bit like ripples in a pond and diffracts out like that. So although light does travel in straight lines in a vacuum. We've seen it doesn't travel in straight lines there where it's being transmitted. It can reflect. And here we're finding that light effectively can bend around corners there. Of course, diffraction only happens if you have a certain wavelength here that is greater than the width there. So diffraction is significant if the wavelength is a lot bigger than that width there. So we'll ask ourselves, let's test to see if a certain example of light will diffract. We'll say it has a frequency of 10 to the 10 hertz, and the width of this gap here we'll say is 100 nanometers. Let's see if this light here will diffract. So we know it will diffract if the wavelength is bigger than this width. So let's figure out the wavelength of this light. Wavelength, we said C is equal to lambda f. Therefore C on f equals lambda. 3 times 10 to the 8 on 300 times 10 to the negative 9 is 1 times 10 to the negative... Oops, sorry, that's not the... What am I doing? I just put the width in there. It's 3 times 10 to the 8 over 10 to the 10, which is equal to 3 times 10 to the negative 2, or 3 centimeters. So the wavelength of light is 3 centimeters, and the width is only 100 nanometers. The wavelength is a lot bigger than the width, therefore we will see diffraction. The next thing we're going to work on is whether light is actually a wave or is actually a particle. Because examples like this here indicate that light is a particle. It's something that's colliding with the electron and bouncing it up. But examples like this support the idea it's a wave. And that is the wave-particle duality of light in physics.